Everyone, and today we are going to talk about the geometric sum formulas and when we should use them. Now, we've talked about sums before already and using sigma notation, and that's our starting term number, ending term number, and the rule that we plug into. So for this first series using the sigma notation, if we plug in 1 to our rule, our output value is 10, plug in 2, plug in 3, plug in 4, and then our last term 5, we get our 5 different values in our series that we can then add together to get our total sum. In our second formula, this one appears to be geometric. We plug in, again, our first term all the way through our ending term 5 into this rule. So we plug in 1, 4 times 3 to the first power is 12, 4 times 3 to the second, 4 times 3 to the third, 4 times 3 to the fourth, and then 4 times 3 to the fifth. We get our 5 terms this time and a total sum of 1,452. So again, just a reminder, what is a series? Well, our series is when we take those commas in our sequence and we change them into plus or minus signs, then our sequence is going to become what we call a series. And again, if this pattern continues, the series, it's possible to find the sum of the first n terms. Now, we can do it where we list out the terms like we did up above, and just add together those values. But it's not really practical because as time goes on, if there's more and more and more terms, if there are many terms to add together, then that's not really going to be super conducive to time and finding all those sums. So again, if we know that we have an arithmetic or geometric, we know that we can sum up our values using a formula. Now, we've talked about the arithmetic one, right? SMN from an arithmetic standpoint, where we take n divided by 2, first term for plus the last term in this amount we're trying to add up. So we've talked a lot about that. We also can do this, though, for a geometric. Okay? And this time what we need is the first term. And then you're going to take 1 minus your common ratio to the number of terms. We are going to add up. Notice just the r gets raised to that n value. And then divide it all by 1 minus the common ratio. And again, the main thing that we need here is the common ratio and our initial term value. In this case, a sub 1, they would just call that. So if we look then at our first 10 terms, they want us to do 2 things here. Number 1, put our series in sigma notation and then find the sum. So notice each time if we take term 2 divided by term 1, each time our common ratio is going to be 0.7. So if we want to express this in sigma notation, this time we are starting at term 1, adding up the first 10 terms, and our rule is our first term times r to the n minus 1 power. So there's our sigma, which again is part 1 of this. And if we want to then add up our first 10 terms, we're going to take s sub 10, 1 times 1 minus our r value of 0.7 to the 10th power, all divided by 1 minus that r value of 0.7. So we type this in the calculator. First term, 1 minus our r value to the n power, which in this case, again, is going to be 10. And then we are going to divide that by, make sure you use parentheses here, 1 minus 0.7. Parentheses, and we have about 3.24 is approximately the sum that this will add up to be. In our second one, notice they're kind of giving us the rule in a way here. And our r value is being represented here this time is negative 2/3. To find our first term, then, we can plug in to our rule 7 times negative 2/3 to the first power. So if we take 7, parentheses, negative 2/3, to the first, we find out our first term this time is negative 14 thirds. So this time we kind of have the R value, but we're looking for that first term by plugging it into the rule. So if we're adding up the first 15 terms this time, we have our starting at term 1, ending at term 15. And again, they're kind of giving us the rule this time that we are able to plug in, which is the 7 times negative 2 thirds to the k power, the n power. You could have also done the first term times the r value to the n minus 1 power. Either way works, again, for that. Now to find then the sum of our first 15 terms, we're going to take that first term, negative 14 thirds, 1 minus our r value to the 15th power, and then all divided by the 1 minus our r value. So again, be very careful. Half the battle here sometimes is just typing this into the calculator. So we have our first term, which was negative 14 thirds, and then again 1 minus parentheses negative 2 thirds. I'm going to make sure I use parentheses so I make sure that negative gets raised this time to the 15th power. And then you can either type it all in as one step, or I'm just going to take divided by, again, make sure I'm using parentheses here, 1 minus our r value. And again, we get about negative 2.81 is about what we're getting on this one is our final answer. So approximately equal to negative 2.81. Now, sometimes you're going to notice once again that our series might flip-flop. And again, to find that R value, don't be afraid of seeing that changing sign, because all that's really meaning for us is that our R value is negative this time. In this case, it's negative 3. And the sum of those first 7 terms, first term, 1 minus that R value to the 7th this time, and then all divided by 1 minus the R value. This time we're actually going to get a sum of a negative value, which is sometimes possible, right? If we're adding up every other one being negative, sometimes that's going to happen. And in this case, our value is negative 1,094. Okay. There is one similar to that for you to try as well in number 4. Now, we sometimes are going to add up what we call a finite number of terms. And a finite number is a specific number of terms. Sometimes our geometrics are going to be able to add up an infinite amount of terms. So think about this situation where we have Taylor Swift concert tickets for a show in California. The show isn't until next year, so we have plenty of time. If you go to O'Hare to LAX is approximately 2,028 miles. And if you go halfway each day, how long would it take you to get there? Well, if we think about this, right, if we took 2028 and day 1, we divide this by 2. Day 1, we would have to be at 1,014 miles away. Divided by 2 then. Day 2 would be 507 miles away. Day 3 would be 253.5. And what we're noticing, though, is that if we keep going on and on and on, we're going to get infinitely close to 0, but at this rate, we're never going to actually hit 0. We're just going to get infinitely close to it, right? So sometimes we're going to see these series that never officially end, right? And what we can do then is, because these are converging to a certain value, this is what we call an infinite series. And with these geometrics only, this is going to be able to be summed up to a certain value because of this. Now, when is this going to happen? Very, very important clause here. It's going to happen when our R value is between 0 and 1. Okay. It can be positive, it can be negative. So sometimes you're going to see it represented like this, or again, you sometimes see it as the absolute value because it can be negative, but that r has to be between 0 and 1 if we say absolute value. Okay, or another way of thinking, between -1 and 1, but you're not going to have your r value equal to 0. Okay, so how do we actually calculate this? Well, it's a similar formula to the one we had before, sum of an infinite. We're going to take our first term, so a sub 1, and then 1 minus our r value on this is all we take. So again, you just need the first term and the r value because of the way these are converging. So here's some sample problems, right? If we check this out, first and foremost, you're always going to want to check your r, right? Because if the r value is not in between -1 and 1, it's not going to work out. So if we check out this example, 1/3 is our r value this time, so this is going to work out. And then we plug in our first term and our r value, and we see that our series is converging to 54. Now, why is this working out like that? Well, if we check out Desmos right now, we could look at that one. If we check out Desmos, so again, in this particular series, our formula for this would be our first term, 36, our r value of 1/3, and then we would say to the n minus 1, or in this case, x minus 1 power, right? And what we notice is that as our r values are getting bigger and bigger and bigger, we're converging towards an actual value, and this is what's allowing us to actually sum these up. So we could see why that's working out. Okay. Now we also can express this in sigma notation. Notice now what's happening is up top we have that infinite series happening, so that's why we know we're going to want to use this particular formula. Okay, so that's another way to know that you would use this formula as opposed to the finite formula. So if we check out a couple more examples here, okay, we see in this first one, if we check out, is this r value going to work out? Well, if I take term 2 divided by term 1, so if I take 4/9, put that in parentheses, divided by term 1, which is 4, I have an r value of 0.1 repeating, or 1/9. That is, in fact, in between -1 and 1, so we are good to go there. So now I can actually calculate that infinite sum, take my first term, divided by 1 minus that r value of 1/9, and if we take 4 divided by 1 minus 1/9, we get 4.5, or 9/2, depending on how you write that, as our value of our infinite sum. In the next one, okay, notice our r value this time, if we take term 2, which is -1/2, divided by term 1, which is just 1, we have an r value that, again, -0.5, is between -1 and 1, again, not equal to 0. So even though it's a negative r value, it's still a decimal in between -1 and 1. So we can take, to find the sum then, our first term divided by 1 minus that r value of -1/2. So 1 divided by 1 minus -1/2 is 0.6 repeating, or 2/3 would be our sum. All right, on our next example, we have to check the r value. So we're going to take term 2 divided by term 1. Well, 1 divided by the fractional value of 1/2 is 2. This is no bueno, right? Because this is not between -1 and 1. It's too big, right? So this is going to be an example when it would not be possible to find that infinite sum, because it would not converge towards a particular value. So again, that R value is too big. Try this last one on your own. Find the R value and then calculate the sum if possible. Thanks everyone for watching. We will work more with our geometric sums, both finite and infinite, in class.